In the last video, we talked about using binomial PDF to find the probability of exactly X successes in N trials. But sometimes we don't necessarily want to know the probability of exactly X successes. We want to know the probability of at most X successes or at least X successes. How do we do that? Well, the cumulative um, binomial CDF is the cumulative probability function on the calculator, and the C stands for cumulative. That means it adds up several probabilities for us. On the TI-8384, the command binomial CDF and then the same arguments N, P, and X on the calculator provides the sum of all probabilities from x equals 0 through the specific value entered for x. So it's going to, if I type in the probability of, let's say, binomial CDF 10, comma, 0.3, comma, 7, then the calculator is going to add up the probabilities from 0 through 7. X is where I tell the calculator to stop adding. In other words, to find the probability of at most X successes in N trials, if each success has a probability of P, go to second and VAERS, that's the distribution menu again, scroll down to B, which has binomial CDF, and then press enter. After you enter the values of N, comma, P, comma, and X, and then enter again. For example, if the probability of an individual having group O blood type is 0.45, find the probability that at most 2 out of 5 randomly selected donors would have group O blood. Now, if I just selected 5 people and said how many of these 5 people have group O blood, then the answers would be either none of them do, or all of them do, or somewhere in between. I want the probability of at most 2. At most 2 means 2 or less. And out of 5, at most 2 would indicate either 0 or 1 or 2. I want to add up the probabilities of 0 or 1 or 2, and that's when I use binomial CDF. N is the number of trials, P is the probability of having group O blood, because that's what we called a success, and I want the probability of at most 2. So 2 is where I want the calculator to stop adding up the probabilities. Binomial CDF 5, comma, 0.45, comma, 2 gives me a probability of about 0.593. So in other words, if I selected 5 donors, there's about a 60% chance that no more than 2 of them would have group O blood. Now you have to read very carefully to know how to find each probability based on whether it says find the probability of exactly X successes or at most X successes, or perhaps we'll even run into at least X successes, and we'll talk about that in just a minute. But when I want the probability of exactly X successes, that's when I use binomial PDF and enter the arguments N and P and X in that order. Binomial CDF gives me the probability that there are at most X successes. That adds up all the probabilities from 0 to whatever X value I enter at the end of that argument. For example, if P is 0.2 and N is 8, circle the numbers which are implied by at most 5. At most 5 means the same thing as 5 or fewer. And so at most 5 out of 8 refers to 0 through 5. What would you enter on the calculator to find the probability of at most 5 successes? We don't want exactly 5 successes, so we're not going to use binomial PDF. We're going to use binomial CDF and enter the number of trials, 8, the probability of success on one trial, 0.2, and the x value is the last value whose probability I want the calculator to add in. I want it to stop adding at 5. So binomial CDF, eight, comma, 0.2, comma, 5 is about 0.999. That's the probability of 5 or fewer successes out of 8. Now there's one other scenario. We've talked about exactly X successes or at most X successes. What about at least X successes? At least X means X or more, X or X plus 1 or X plus 2, or so on. For example, circle the numbers which are implied by at least 6. At least 6 includes 6 and everything bigger than 6. Now, this is not the probability that the calculator will give me. Binomial CDF always starts at 0 and adds until I tell it to stop. It won't start with 6 and add to where I tell it to stop. So somehow I have to figure out how to get the probability of at least 6 using what the calculator will give me. Well, notice that if at least 6 means 6, 7, or 8, the complement of that is 0 through 5, and that is what the calculator will find for me. I can find the probability of 0 through 5 by using binomial CDF, out of 8 trials, each trial having a probability of 0.2. What's the probability of at most 5? And that will give me this probability, which is the complement of the probability I want. If I have this probability and I want that probability, just subtract the probability I have from 1, and you can enter that straight left to right on your calculator. Make sure you're choosing binomial CDF. What's the probability that out of 8 trials, each having a probability of success of 0.2, what's the probability of at most 5? That's, well, actually, that's the 0.999 that we came up with just a minute ago. So the probability of at least 6 is 1 minus that, or 0.001. When you want the probability of at least something, you're going to have to find the probability of its complement and then subtract that probability from 1. All right, let's do a few more examples. If success is defined as having group O blood and the probability of success is 0.45 on a single trial, find the probability that at least 3 of 5 donors have group O blood. If I randomly choose 5 people, then the answer to the question, how many of them have group O blood, would be either 0, 1, or 2, or 3, or 4, or 5. If I want the probability of at least 3 means 3, 4, or 5. But that's not what binomial CDF will give me. Binomial CDF is going to add from 0 up to wherever I tell it to stop. That's the complement of what I want. So all I have to do is find this probability with binomial CDF out of 5 trials, each having a probability of success being 0.45. What's the probability of at most 2? And once I have that probability, I can subtract it from 1 to get the probability that I'm looking for, the probability of at least 3. And by the way, you can enter that straight left to right on the calculator. You can say 1 minus before you pull up binomial CDF. And then go ahead and enter the size of the trial is 5. Probability of success is 0.5. And I want the calculator to stop adding at 2. So 2 is the last number I enter. And that probability rounds up to 0.407. The probability of getting at least 3 out of 5 donors with group O blood, there's about a 40% chance of that happening, maybe 41%. If I have to have 3 pints of group O blood, is it very likely that I'm going to get all 3 pints from just choosing 5 donors? Well, there's about a 40% chance that I will, but there's about a 60% chance that I won't. I would say no. There's about a 60% chance that less than 3 will be obtained. No, actually, it's 59%, but I'm just trying to answer this question as simply as I can. All right. One more problem involving finding probability. A medical testing laboratory saves money by combining blood samples for test so that only one test is conducted for several people. If combined sample test positive, if at least, let me try that again. The combined sample test positive if at least one person is infected. If the combined sample tests positive, then you have to go back and do individual tests. But medical laboratories save a lot of money with batch testing for diseases that are fairly rare. This one just happens to be about gonorrhea, and the probability of a randomly selected person having gonorrhea is 0.00114. That probability is so low that rather than doing blood test on every single sample, the CDC will combine 30 samples and test that combined sample. If everybody in the sample is clean, nobody has gonorrhea, then the lab has saved a lot of money by only having to conduct one test rather than 30. However, if the batch test comes back positive, then the CDC has to go back and do individual tests on the groups of 30. Find the probability that no one in the sample is infected. Well, does no one mean at least something, or at most something, or exactly something? Find the probability that no one is infected. Sounds like the probability of exactly 0. And if I want to find the probability for exactly 0, I would use binomial PDF since it says exactly. And I would say out of 30 people, each having the probability of 0.00114 of having this disease, what's the probability that exactly 0 of them do? I got that to be about 0.966. That means about 97% of the time, the whole batch comes back testing negative, which means no one in that group has gonorrhea, and the labs just saved a lot of money by conducting only one test instead of 30 tests. We also need to find the probability that the combined test positive with at least one of the 30 people infected. Well, there's an easy way to do this and a less easy way to do it. We could say at least is 1 minus binomial CDF and add up from 0 to 29, or we could just say at least 1 is the complement of none. Either none have gonorrhea or at least 1 does. So we already have this probability of at least 1 is 1 minus the probability of 0. And we said the probability that no one, that the whole batch is negative is 0.966. So the probability that at least one person in the batch of 30 is infected is only 0.035. In other words, about 97% of the time, the batch test will be negative. About 3.5% of the time, the batch test will be positive, and we'll have to go back and do individual tests. The final question is it likely that such combined samples test positive? Well, that 0.034 is less than our cutoff for what we consider usual. So I would say it's unlikely or unusual that the batch test would be negative. Excuse me, I'm sorry, unusual that the batch test would be positive. All right, there's one other thing we need to talk about. In 5.2, we found the mean of a probability distribution. So we should be able to find the mean of a binomial probability distribution and also its standard deviation and its variation. We just need to be able to interpret these values and use them to say whether a certain value is unusual or not unusual. The formulas that you need for binomial distribution parameters are the mean. The symbol for the mean of a probability distribution is mu, and the mean is just the number of trials times the probability of success. Think about it this way. In 5.2, we said expected value means the same thing as mean. If I say I have a population of, or a sample of 100 people, and 15% of them have blue eyes, how many would you expect to have blue eyes? You would just say 15% of 100 is 15. So the expected value is 15. That means the mean is 15. The variance, symbol for variance, is sigma squared. The variance is n times p times q. Remember, q is the probability of failure. And then the standard deviation is just the square root of the variance, the square root of n times p times q. Just as we have been doing, if we want to find a range of usual values, you can say the highest usual value is the mean plus 2 standard deviations, and the lowest usual value is the mean minus 2 standard deviations. Anything within that range is considered usual. Anything outside that range would be considered unusual. Mars Inc. claims that 24% of its M&M plain candies are blue. A sample of M&Ms is randomly selected. Find the mean and the standard deviation for the numbers of blue M&Ms in such groups of 100. Well, we're given that the sample size is 100, and Mars says the probability that any individual M&M is blue is 0.24. So if I just said, how many blue M&Ms are you expecting? You could say 24% of 100 is 24. In a group of 100 M&Ms, I'd expect 24 of them to be blue. That's just really the definition of percent. If you had a problem that you could not do that in your head, you would say the mean is n times p, or 100 times 0.24, and get that the mean is 24 blue M&Ms. And remember that that means the same thing as expected value, the number of blue M&Ms I would expect to get in a bag of 100. I'm also supposed to find the standard deviation. Let me do that out here. The standard deviation is the square root of n times p times q. For this problem, that's the square root of n is 100, p is 0.24, and q is the complement of p. If the probability of a blue M&M is 0.24, the probability of a not blue M&M is 0.76. So the square root of 100 times 0.24 times 0.76 is about 4.3. So I'm expecting 24 blue M&Ms with a standard deviation of 4.3. Let's go ahead and get the minimum number of blue M&Ms and the maximum number of blue M&Ms. Remember that the minimum is the mean minus 2 standard deviations, and the max is the mean plus 2 standard deviations. So for this problem, the minimum number of blue M&Ms would be 24 minus 2 4.3s. That's 15.4. And the standard and the maximum usual number of blue M&Ms would be 24 plus 2 standard deviations, or 32.6. That means I'm not going to be surprised if my bag of 100 M&Ms has between 15.4 and 32.6 blue M&Ms, but 10 would be surprising, unusual, because it's less than the minimum usual value, and 40 blue M&Ms would be unusual because it's more than the highest expected or highest usual number of blue M&Ms. The question in the B part is, would 27 be unusual? Well, 27 is between this minimum usual and maximum usual. So I'm going to say no, 27 blue M&Ms would not be unusual. If you ask me for a number that would be unusual, I would just say any number less than 15.4 or any number greater than 32.6. Does it seem if I did get this bag of M&Ms, 100 M&Ms, and it had 27 blue, would I think Mars was lying to me, that that claimed rate is wrong? No, because 27 would not be an unusual number of blue M&Ms, even if the rate of 24% was correct. We have one more problem, and it illustrates how sometimes statistics are used to scare people. I remember when there was a concern about whether or not cell phones use cause brain cancer. So, a group in Denmark studied 420,095 cell phone users, and it was found that 135 of them developed cancer of the brain or nervous system. At first glance, that's very scary. I wonder if using the cell phones caused these 135 to develop brain or nervous system cancer. Well, medical researchers, medical researchers, I can't say medical researchers. Medical researchers tell us that the probability of developing that particular type of cancer, whether you use cell phones or not, is 0.00034. So even if you had never held a cell phone to your ear, there's still a chance that you would develop that type of cancer. Let's see how many people we should have expected to get that type of cancer out of that study group, even if the cell phones were having no effect on the cancer. Well, expected value again means mean, and the mean is the trial size or sample size times the probability of success. Since we're studying the number of people who develop cancer, we're saying developing cancer actually in this situation is success or this type of cancer. And the probability of success is 0.00034. So the number of people that I would have expected out of that 420,000, the number that I would have expected to develop that type of cancer, rounded to the nearest whole person, is 143. Actually, fewer people developed cancer than we would have expected to, even if the cell phones didn't have anything to do with the development of that type of cancer. We also want to find the standard deviation. That's the square root of the 420,095 times the 0.00034 times the complement, or 1 minus 0.00034. And I got that to be about 12. Notice if one standard deviation is 12, then two standard deviations would be 24. So I really wouldn't be surprised if between 143 minus 24 or 143 plus 24 people had developed that cancer. I would say the max, or I'm going to call it just the usual range, the mean plus or minus 2 standard deviations. 143 minus 2 standard deviations is 119, and 124, no, I'm sorry, 143 plus 24 is 167. Anywhere in that range would not have been considered an unusual number of people to develop this type of cancer. So in the B part, based on our results, is it unusual to find in that sample there were 135 cases of that type of cancer? No, that was within 2 standard deviations of the mean. And what do these results suggest about publicized concern that cell phones are a health danger because they increase the risk of cancer? I'm just going to say that's bogus. I would have actually expected more than 135 people out of this sample size to develop that type of cancer, even if they had not used cell phones. All right, just to recap what we've talked about in 5.3 and 5.4, you should be able to identify the probability, binomial probability distribution. You should be able to find the probability of X successes, exactly X successes, or at most X successes, or at least X successes in N trials. You should be able to find the mean, the variance, and the standard deviation of a binomial probability distribution, and you should be able to identify usual and unusual outcomes. So that's it for 5.3 and 5.4. That's actually all the material that is covered on test 2. So you're ready to begin the practice test. Let me know if I can help.